let's go ahead and continue where we were last time. So last time we had talked about some of the functions, so some of the derivatives of trigonometric functions. Specifically, the derivative of sine is cosine. The derivative of cosine of x is negative sine of x. And the derivative of tangent of x is secant squared of x. And I do feel like it is in our interest to finish off this list with the other three trig functions. Let's go ahead and find the derivative of cotangent. And I'm going to point out that for cotangent, secant, and cosecant, we really do all of them using the quotient rule. Now it's interesting. I've never done it this way, but some people like to find the derivative of cotangent. I would always think of it as the derivative of cosine of x over sine of x. But other people, that might dx, that looks terrible. But other people think of it as the derivative of 1 over tangent of x. And both are totally correct. If I was doing it, well, I would do it this way because that's the way I'm used to doing it. But I actually think it's easier to do it this way. Let's go ahead and find the derivative of 1 over tangent using the quotient rule. Thanks. Let's see. So doing it this way, it's going to equal the bottom. Thanks. Times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is secant squared x, all over the bottom squared, which is tangent squared x. So I end up with, let's see, negative secant squared of x over tangent squared of x. Now, this is going to be something we should simplify because looking at, right, that's not the answer we want to write out. So I'm going to change everything to sines and cosines. I'm going to write this as negative 1 over cosine squared of x all over sine squared of x over cosine squared of x. And then what can I do? Well, you can either think of just canceling the cosines, or you could think of flipping this to bottom thing over and multiplying by it. So this can be negative 1 over cosine squared of x times cosine squared x over sine squared x, which is equal to negative 1 over sine squared x, or more typically as negative cosecant squared of x. So if your function is cotangent of x, its derivative is negative cosecant squared of x. Thanks. We'll do the last two, and then we'll talk about a couple different ways to remember all 6 of these trigonometric derivatives. So let's do secant. And just, I feel like I've said this before, but let me say it again anyway. This notation just means the derivative of secant of x, or the derivative with respect to x of secant of x. People could, although don't typically, you could also write this as d secant of x in the numerator over dx, like that. So it's kind of like dy dx. People don't usually write it that way. This is the typical way of writing the derivative of whatever your function is. And that's just the most, I don't think it's the most common, it's the easiest to write. So that's kind of why it's probably the most common. This looks really, I feel like I'm just off kilter a little here. 1 second. There we go. That feels a little better. All right. Again, we're going to rewrite this as a quotient. So the derivative secant of x is the derivative of 1 over cosine of x. Now we're going to use the quotient rule. Bottom times the derivative of the top. The derivative of 1 is 0 again. It's always going to be 0. Minus the top times the derivative of cosine is negative sine of x, all divided by cosine squared of x. And I'm going to get, let's see, 0 minus 1 times minus sine is positive sine of x over cosine squared of x. And just like before, we're not going to leave the answer like this. Instead of writing it as sine of x over cosine squared of x, I'm going to write it in a very particular way. I'm going to write it as 1 over cosine of x times sine of x over cosine of x. And then what's 1 over cosine also known as? Sorry, what was that? Yeah, secant. I know you guys are probably saying the right thing, but sometimes my hearing's not always great. One of those advantages of getting old or disadvantages of getting right. And what's sine of x over cosine of x? Right. Tangent of x. And that's typically how we write the derivative of secant of x, is secant of x times tangent of x. And finally, the derivative of cosecant is very similar. The derivative of cosecant of x is going to be the derivative of 1 over sine of x. Again, the quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom, which is going to be cosine of x, all divided by the denominator squared, which is, oops, not cosine squared. Sorry, that should be sine squared. Sorry, I got a little carried away there. And then I get a negative cosine of x all over sine squared of x. I'm going to break that up in a similar way. I'm going to do this negative 1 over sine of x times cosine of x over sine of x, which we're then going to rewrite as negative cosecant of x times cotangent of x. And those are your 6 trigonometric derivatives. So let's write them all out in a little table so that we can remember them. So got your function, got your derivative. Derivative of sine of x is cosine of x. Cosine of x is sine of x. And I'm going to say a couple things here to help, hopefully help. Derivative of tangent of x is secant squared of x. And now I'm going to write some words here just to help. Ooh, that's interesting. It's got some red on it. Huh. Interesting. Got some leaky pens. All right, well, we'll deal with that later. Which of you red pens is the problem? All right, so I want to point out, and I'm going to write some words because it makes it easier to see. The derivative of tangent of x. I know nobody writes tangent the whole word. Okay, question. Oh, thank you. Yes, there's a negative value there. There's a negative, yeah. And actually, more generally, here's a pattern you can always count on for trig functions. The co-functions, cosine, cotangent, cosecant, all have negative derivatives. So I should have definitely seen that. But yeah, totally. So derivative cosine is negative, derivative cotangent is negative, derivative cosecant is negative. The other 3 are positive. But here's what I want to show you in conjunction with that one little pattern. The derivative tangent of x is secant of x. And again, I know it's kind of weird to write out the whole word, but just wait. I'm going to write that down again, and I'm going to add something to it. Sure, using red pens. The derivative of cotangent of x is negative. Oh, I forgot the squares. God, I'm just forgetful today. Sorry, apologies. The derivative tangent of x is secant squared of x. The derivative of cotangent of x is negative cosecant squared of x. So for a non-co function like tangent, you can find the derivative of cotangent, but just throwing a co on everything. And it also works for the other ones, meaning, check this out. We know, excuse me, that the derivative of secant of x, let's get it right, James, is secant of x times tangent of x. Again, I know I'm going to write out some long words here. The derivative of secant of x is secant of x times tangent of x. And then I'm going to do the same thing, but I'm going to leave space in front of each trig function. So the derivative of cosecant of x is cosecant of x times cotangent of x, but negative. Thanks. Sorry, can you see that? Of course not. So if you know the derivative of a regular trig function, you know the derivative of its cofunction just by throwing a co on it and adding a negative. And it even kind of lamely works for sine and cosine. It's not as exciting, but you can say the derivative of sine of x is cosine of x. And although this might feel kind of dumb, it does work. The derivative of cosine of x is negative cosine of x, and cosine is sine. Cofunction of a cofunction is just a function. So for any regular trig, regular meaning the non-cofunctions, for each of these, you can just tack on the co in front of each of the trig function names and get the other derivative. So a lot of words to say. You can memorize less. If you memorize these three, memorize the derivative of sine is cosine, then you can be like, oh, well, then the derivative of cosine is negative cosine, which is okay, that one you probably just want to memorize these two anyway. But then you really only have to know tangent and secant, because if you know the derivative of tangent is secant squared, you know the derivative of cotangent is negative cosecant squared. And similarly, if you know the derivative of secant of x is secant of x times tangent of x, then the derivative of cosecant of x is negative cosecant of x times cotangent of x. It's a nice way to have to remember less. Maybe you think it sucks. That's also fine. But whatever you do need to memorize these 6 trig derivatives. They come up often enough that you should just memorize them. I feel like these 2 are pretty easy. Like we use these ones all the time. These other 4, you should spend a little time too. Something I've told my students to do in the past is to make it the background of your phone or your lock screen, so that when you look at your phone every time, you're like, oh, there's the 6 trig derivatives. Let me take a look at them real quick. Like it's definitely something I've done for other math things that I couldn't remember. And it's really, I mean, as a teacher, not as a student, because we didn't have such nice phones when I was a student. But as a teacher, there was like one class I was teaching, I was like, oh, I can't remember this stuff. It's really hard to get. So I made it the lock screen of my phone. And I looked at it every time. I'm like, oh, I'm getting it now. It makes sense. I'm remembering it. So trying to remember something, it's not a bad idea. One other thing, and then we'll move on. A student showed me that they did this one time, and I thought it was pretty cool. They made this little table graph, I don't know. They made this little diagram. Oops, tangent of x, sorry. So what this diagram was saying to them was that the derivative of secant is secant times tangent. And the derivative of tangent is secant times secant. And then it also works for cosecant. The derivative of cosecant is negative cosecant x times cotangent x. The derivative of cotangent is negative cosecant x times cosecant x, which is negative cosecant squared. So that's an alternative way you can remember these things if you want. So lots of ways to remember the trig derivatives. Pick your poison. Do whatever you want. So this day is looking much more beautiful than it looked like it was going to be at the beginning. I should remind you, or not remind you, just let you know, there's a handout up there at the front for when you leave. It's got like extra practice problems to work on, and there are solutions posted to it on Grant's website. So if you're looking for more practice with like the product rule, the quotient rule, the chain rule, which we're going to talk about today, then those are some good practice problems. Obviously not required, but encouraged. Yeah, let's see here. Let me do one more thing. I'm really liking my new pens. They're working out great. I'm very excited about them. So let's do a problem that looks like the product rule, but is really something else in disguise. So let's use the product rule to find the derivative of this function. And let's call it, sure, of x equal to x to the 5th plus 1 cubed, which I'm going to rewrite as x to the 5th plus 1 times x to the 5th plus 1 times x to the 5th plus 1. When I have to remember, did we talk about the triple product rule? Okay, we'll come back in just a sec. Sorry. Talked about it in the other class. I forgot it here. So triple product rule. We know the regular product rule. If you take the derivative of the product of two functions, it's the first derivative times the other function left alone, and then you switch it up. You leave the first function alone, multiply by the other one. And just as a reminder, right, an example of this could be something like taking the derivative of x cubed times cotangent of x and getting 3x squared times cotangent of x plus x cubed times the derivative of cotangent, which is negative cosecant squared of x, which I would write as 3x squared cotangent of x minus x cubed cosecant squared of x. And that's how the product rule works, right? You have functions multiplied together. Derivative, I always think of it as the derivative of one piece times the not derivative of the other piece plus, and then you switch it. You do the derivative of the other piece and the not derivative of the first piece, or vice versa to say it much more quickly. But you can also do a product rule derivative for any number of things multiplied together. So if I want to find the derivative of, say, a product of 3 functions, how do I do that? Well, what I do is I treat it like 2 pieces. So just for a moment, I'm going to say that f times g, I'm going to call it another name. Let's call it, I don't know, j. I like the letter j. So now I'm really taking the derivative of j times h. And now I can use the regular old product rule. It's going to be the derivative of j times h plus, and then we switch it up. We do j times h prime. Okay, but now we're going to remind ourselves that j is really the function f times g. So that when I write this, this is actually f times g prime times h plus f times g times h prime. And now we're going to also use the product rule for the derivative of f times g. And we're going to get f prime g plus f g prime all times h plus f times g times h prime. And then if we finally distribute this, we get f prime times g times h plus f times g prime times h plus f times g times h prime. And it helps to put parentheses just to separate them out. And you can extend this idea to any number of things multiplied together. I don't want to really do it, but I'll do it for one more. And I'm not going to do the long one, I'm going to do the short way. So product of 2 things, great. Product of 3 things, great. If you have the product of 4 things and you wanted the derivative, here's how it always works. I have 4 things multiplied together. I'm going to get 4 pieces. And in each piece, just like here, you're going to get one function's derivative and the other function's left alone. So here I'm going to get f prime times the other 3 left alone. Plus, now I'm going to get g prime times the other 3 left alone. Then I'm going to get h prime times the other 3 left alone. And then I'm going to get j prime times the other 3 left alone. And that's how the product rule for a product of any number of things works. You always get that many pieces added together, and in each piece you get one derivative and the rest not derivatives. And all of the functions, each derivative has to show up at least once. So you have to have f prime and g prime and h prime and j prime. So you can do it for 6 things, 8 things, 100, right? It would be terrible, but that's kind of the idea. Okay. So now that we've got the triple product rule, the quadruple product, any number of product rule things you want, let's go back to this. Let's take a sip of water. Sorry, we'll dry it. So I'm going to use the triple product rule to take the derivative of x to the fifth plus 1 times x to the fifth plus 1 times x to the fifth plus 1. And let's see what happens. So it's going to be the derivative of the first piece times the other pieces left alone plus the derivative of the second piece times the first piece times the third piece left alone. And then finally, the first two pieces left alone times the derivative of the third piece, which is also 5x to the fourth. And as you might recognize or observe, each of these things are the same. This whole thing, this whole thing, and this whole thing, those are all the same. When you have the same thing added together 3 times, you get 3 of that thing, right? X plus x plus x is 3x. So this is really going to be 3 times this quantity, which I'm going to write in a slightly different way. My equal sign seems way off base there. I've got x to the fifth plus 1 times x to the fifth plus 1. So I'm going to have x to the fifth plus 1 squared times 5x to the fourth. And now here's what I really want you to see if you haven't seen it before, or even if you have seen it before. What I did was I had my function f of x. Instead of saying it's x to the fifth plus 1 cubed, I'm just going to say it's some stuff cubed. The stuff in this particular problem happened to be x to the fifth plus 1. And the derivative ended up being 3 times that stuff squared and then what did we multiply by? What do we have out here? Right, exactly. Thank you for knowing the answer to the question I wasn't asking very well. Exactly, the derivative of the stuff. Like all this multiplying out stuff? No. So the whole point of this wasn't that you're ever going to do it this way. You were never going to do it this way. The whole point of this was to show you how we get to the chain rule. Because this is the idea of the chain rule, is that when you have some stuff raised to a power, you take the derivative of the outer function in the usual power rule kind of way, 3 times whatever to the second power. If the original function is something cubed, you get 3 times something squared. Well, then you have to multiply by the derivative of the inside something. And this is really showing that, right? We literally use the product rule to get this. Now, you could have done this another way if you really wanted to. You could have actually multiplied the whole thing out. That would also work, and you would also get the same result. But I don't think it's quite as illustrative, so that's why we did it this way. But I want to just reemphasize, it is literally true that if you take the derivative of x to the fifth plus 1 quantity cubed, you get 3 times x to the fifth plus 1 squared times 5x to the fourth. And more generally, this actually isn't as general as it gets, but oops, sorry, I keep going the wrong way here. I'm like, what am I doing? Okay, sorry, paper's over here. That paper's terrible. Why do I have all this weird paper in my, sorry. My paper's like funky. Yeah, it's all like facing the wrong way. Face the right way. There we go. Great. So more generally, if you have your function is some other stuff raised to the pth power, then the derivative is going to be, well, the derivative of x to the p is p times x to the 1. So the derivative of some stuff to the p is p times your stuff to the p minus 1 times the derivative of your stuff. Sorry, I feel like I might have said before the derivative of x to the p was p times x to the 1. I meant p minus 1 if I said it incorrectly. Sorry. That's the generalized version of the power rule, or what we call the chain rule version of the power rule. This is not the chain rule completely, but it's how the chain rule works. You take the derivative of the outer function, in this case being raised to the pth power. You leave the insides alone, but then you multiply by the derivative of the insides. So for example, let's say we had something like, let's say if this, then this. let's say we had something like f of x equal to x to the 4th plus 6x to the 10th, which you could use a 10 times power or product rule for. You're not supposed to, right? That's not the point. The whole idea here is that, oh, this is some stuff to the 10th power. And the derivative is going to be, I always think of it as I've got something to the 10th. I know the derivative of x to the 10th is 10 times x to the 9th. I know the derivative of some stuff to the 10th is 10 times your stuff to the 9th. But then what do I have to multiply by? Always the derivative of the stuff. So if you're saying you've got some stuff that is more complicated than x, whenever you do the derivative of it, you always have to multiply by the derivative of that stuff. So I would try to get yourself into the habit of saying, not the function. Don't say I've got x to the 4th plus 6x to the 10th. Just say you've got stuff to the 10th. And then be like, oh, the derivative of stuff to the 10th is 10 times stuff to the 9th times the derivative of the stuff. I'm going to say stuff like 1,000 times in class. Like stuff is the word I use all the time. It's even good if your stuff is lame, meaning not lame, but not exciting. For example, if we have g of x equal to something like, I don't know, x plus 2 to the 13th power. Even though I know it's not really going to make a huge difference, I'm still going to think of it in the same way. I've got some stuff to the 13th power. My derivative is 13 times my stuff to the 12th power. And what do I have to multiply by? I know it's not exciting, but it is 1, right? It's the derivative of the stuff. Even if it's 1, you should still at least think about it being there, even though we know it's going to be 1. So don't ignore the stuff in its derivative. Also, I want to point out that for this function here, the derivative is not 10 times 4x cubed plus 6 to the 9th. A lot of times people try to kind of take the derivative of this stuff at the same time as taking the outer derivative. It's not the deal, right? The deal is you take the derivative of the outside part, you leave the insides alone. They stay the same, they don't change, and then you multiply by the derivative of the inside. And this derivative of the stuff here is kind of completely separate from everything else, meaning you're just multiplying by it at the end. It's not in the denominator, it's not in an exponent, it's not inside a trig function. It is just there at the end being multiplied by. So let's look at a couple more examples. Yeah, let's say we had something like, what are my next examples here? Oh, sure, that's a good example. Yeah, let's say my function, let's use another page. Let's say we had f of x equal to the square root of x to the 4th plus e to the x plus sine of x. Before I do anything, I'm going to rewrite that as a power. And when you're dealing with radicals and taking derivatives, it's almost always in your best interest to write it as something to a power versus the square root or something, or the cube root or whatever. So let's rewrite this. So it's still f of x. It hasn't changed yet. As x to the 4th plus e to the x plus sine of x, all raised to the positive 1/2 power. And the derivative of that's going to be, well, again, we have some stuff to the 1/2 power. The derivative is going to be 1/2 times my stuff to the negative 1/2. Just using the power rule on the outer part. And then the stuff doesn't change. But then what do I have to multiply by? The derivative of the stuff. Derivative of x to the 4th is 4x cubed. Derivative of e to the x is e to the x. Derivative of sine of x is cosine of x. So I have 1/2 times my stuff to the negative 1/2 times the derivative of the stuff. Do one more and then we'll talk about a few other things. What if my function was cosine to the 6th power of x? what's the stuff and what's the outer function? So when I'm thinking about the outer function, I'm trying to ask myself, what's happening last? It's like if you actually plugged in something for x, so you plugged in pi over 3. And you did cosine to the 6th of pi over 3. Would you do cosine first or the 6th power first? It's a good question. If I was doing cosine to the 6th of pi over 3, it's important to know that this notation is an abbreviation. This is an abbreviation of cosine of pi over 3 raised to the 6th power. We write it this way because it's convenient, right? It's less writing. I don't want to write all of this garbage every time I'm trying to write a power of a trig function. But when we write cosine to the 6th of x, it really does mean cosine of x all to the 6th power, which is very different than cosine of x to the 6th power. So looking at what we've got, I can see that the outer function is being raised to the 6th power, and the inner stuff is cosine of x. So the derivative is going to be, well, the derivative of some stuff to the 6th is 6 times our stuff to the 5th. And then we have to multiply by the derivative of the stuff, which is negative sine of x. And to be careful, you really do need that parentheses there. If you just write like minus sine of x, it's going to look like you mean subtract sine of x. So when you're multiplying by something that's negative, at least at this stage, you want to write the parentheses. And then if I was going to simplify this, which I don't really think you need to simplify these unless you're being asked to do something with them. But if you're going to simplify this, I would simplify it as negative 6 times cosine to the 5th of x times sine of x. Again, I don't think that's really necessary, but if you wanted to simplify, that's how you would simplify it. So one thing the quotient rule lets us do nicely is circumvent the quotient. Sorry, I always often accidentally say quotient when it be chain rule. Apologies, and vice versa. One thing the chain rule lets us do, if it makes sense to, is to completely kind of bypass the quotient rule. It doesn't usually make sense to, but there are a couple instances. For example, specifically, if the numerator is a constant, it is often nice to be like, I don't really want to do the quotient rule. So if my function looks something like 4 over x to the 7th plus 3x plus 2, instead of using the chain, oh Jesus, instead of using the quotient rule, we're going to rewrite it and use the chain rule. So we're going to rewrite as f of x equal to 4 times x to the 7th plus 3x plus 2 to the negative 1. And then we can just use the chain rule. So f prime of x is going to be, well, I've got 4 times some stuff to the negative first, the power comes down. Get negative 4 times your stuff to the 1 less power, so negative second. And then what do we need to multiply by? 7x to the 6th plus 3 plus 0, which I'm not going to write. And if you wrote it like that, you should get marked off, right? If I read it like this, I'm writing it wrong. Because what this really actually says is all of this times 7x to the 6th. And then you add 3 after that. But it really should be the derivative of the outer stuff, leave the inside stuff alone, and then you have to multiply all of this by the entirety of the derivative of the stuff. So if your derivative of your stuff has more than one piece, you should put parentheses around it. If it's just one piece, you don't need parentheses typically. I mean, unless you need to look out for a minus sign like in the previous one. But generally, it's just a good idea to abuse parentheses. Overuse them if you need to make sure that you've got everything multiplied how it should be. But yeah, I think, yeah. So, oh, gosh, my nose itches. Okay, it's 2:45. The chain rule works for any functions, meaning it's not just true if you've got some stuff to a power. It's really true if you've got some function of some stuff. For example, we know the derivative of sine of x is cosine of x. Well, it's also true that, say, the derivative of, I don't know, sine, I don't know why I'm using parentheses there, sine of x squared plus 3 is equal to, well, the derivative of sine of some stuff is going to be cosine of the stuff times. It's true. Works for any function. So if you know the derivative of a function evaluated at just x, you know the derivative of the function where the inside is more complicated than this. And here's what I'm really trying to say. Here's a nice little table of kind of all the rules we need to know. Really, you don't need to write them all out, but it's not a bad idea. So here are the things we know so far. We know that the derivative of x to a power is that power times x to the 1 less power. We have talked about that the derivative of e to the x is e to the x. And then really all that's left after that is the trig functions. Derivative of sine, I mean, that's not all that's left. It's all that's left that's in our wheelhouse so far. There's a few other functions like natural log and a couple other things that we'll learn how to take the derivative. But we've got most of all the derivatives you could ever really take. We got them down. Derivative of sine is cosine. Derivative of cosine is sine, negative sine. Derivative of tangent is secant squared. And I really should be saying of x. Derivative of tangent of x, right? There has to be something, a variable in there. Derivative of tangent of x is secant squared of x. The derivative of secant of x. Oh, but I forgot cotangent. I should keep the list in order. The derivative of cotangent of x is negative cosecant squared of x. The derivative of secant of x is secant of x times tangent of x. And finally, the derivative of cosecant of x is negative cosecant of x times cotangent of x. Well, in each one of these instances, we could replace the x with some stuff. And if we did that, but we have to multiply by it every single time, it's always the answer. It's the derivative of the stuff. So if our function looks like, say, some stuff to the pth power, the derivative is going to be p times our stuff to the 1 less power. And then what do we multiply by? Everybody? Thank you so much. Half of everybody. I know you guys know, you just don't want to say words. It's okay. How about the derivative of e to the stuff? So I'm literally just looking at the previous thing saying, oh, the derivative of e to the x is e to the x. So replace the x with stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff every single time. That's the whole deal with the chain rule. You're always multiplying by the derivative of the inner function. The derivative of sine of some stuff is going to be cosine of the stuff times the derivative of the stuff. And yeah, it's a little tedious to write all this out, but it is worth it. So I'm going to write it all out, even though it's terrible. The derivative of cosine of some stuff is in fact negative sine of the stuff times the derivative of the stuff. So here's what I want to say before we finish this. I'm not memorizing this. In no way, shape, or form have I ever thought about memorizing this table. You definitely want to know all these. Like, these derivatives should be in your heart. You want them there. You want them accessible. You're like, okay, I know in my heart of hearts the derivative of tangent is secant squared of x. Yes, okay. But you should then be able to say, well, if the derivative of tangent of x is secant squared of x, replace the stuff. Replace x with the stuff. So the derivative of tangent of stuff instead of x is secant squared of stuff instead of x. And then since we said the word stuff, we are forced to multiply by the derivative of the stuff. That's it. That's how all of these work. The derivative tangent of stuff is secant squared of the stuff times the derivative of the stuff. And the same goes for the rest. The derivative cotangent of stuff is negative cosecant squared of the stuff times the derivative of the stuff. I also want to emphasize here, the stuff is inside the trigonometric function. You're taking cosine of whatever that is. But the derivative of the stuff is outside of the trigonometric function. It is not being taken the cosine of. All right, the last two are a little wonky. The derivative of secant of some stuff is going to be, well, the derivative of secant of x is secant of x times tangent of x. So the derivative of secant of some stuff is going to be secant of the stuff times tangent of the stuff. The stuff shows up twice. And then we multiply by the derivative of the stuff. Just like the x shows up twice over here, the stuff shows up twice over there. And then the last one, the derivative of cosecant of some stuff is indeed negative cosecant of the stuff times cotangent of the stuff times, of course, the derivative of the stuff. How could you forget the derivative of the stuff? You can't. It's impossible to forget it. All right. So that is how we take derivatives using the chain rule. And we can use it for really anything. I keep trying to put notes in the wrong place here. My goodness, come on. Sorry. So, for example, if my function is e to the 3x, I can't even see 3x. My brain, as soon as I write that, I'm like, oh, that's e to the stuff. And I know the derivative is going to be, well, the derivative of e to the stuff is e to the stuff times what? The derivative of the stuff. And for example, if my function was tangent of x to the 6 plus 8, I know the derivative is going to be, well, the derivative of tangent of x is secant squared of x. The derivative of tangent of some stuff is secant squared of the stuff times the derivative of the stuff. Notice for each of these, for each of these that I didn't write parentheses around the derivative of the stuff because there was only one term. There weren't multiple things added together or subtracted together. So you don't need to have parentheses there. You don't need to have them there. You could, right? There's no crime in adding an extra parentheses here. That's totally fine. That's totally fine. It's just unnecessary. Questions, thoughts, observations? I highly encourage you, when you're looking at these chain rule problems, say the word stuff and say the whole function, right? I know you might read it and just kind of like think what it is, but actually saying that, okay, this is tangent of x to the 6 plus 8. It really pays to say all the words, especially the of. The of is maybe one of the most important words in mathematics. Of, you need to say of. So you're like, oh, this is a function of this other thing. It's a function of x. Function of x squared. For example, what if my function was secant of x squared? Oops, you can't see that. I'm going to find the derivative. You could write the derivative in like 3 different ways. You could say it's y prime. That's probably the easiest. You could also write it as dy dx. Maybe 2 ways. There's probably 2 good ways. All right, I know the derivative of secant of x is secant of x times tangent of x. I know the derivative of secant of some stuff is secant of the stuff times tangent of the stuff. And then what must I multiply by? Yeah, you're like, I don't even know what he's asking, but it's probably derivative of the stuff. Yeah, it's the derivative of the stuff. It's 2x. Our other rules are still applicable, meaning if I have something like f of x equal to x to the 3rd plus 1 to the 7th times tangent of e to the x plus x. Not only do I have some chain rules in there, I also have a product rule. Right? I've got a function times another function. And I know the derivative is going to be, writing out very generically, capital F prime times G plus f times capital G prime. The big F and the little f are not related to each other. Sometimes they're in like Calc 2, there's some notation where little f and big F are kind of related. I'm just using a capital to differentiate between them, right? There's no relation between little f and big F. So now I'm going to say, well, I need to find the derivative of big F. So I'm going to take the derivative of x to the third plus 1 to the 7th. And I'm going to use the chain rule. I've got some stuff raised to the 7th power. Its derivative is going to be 7 times my stuff to the 6th times the derivative of the stuff. The stuff is x cubed plus 1. The derivative of the stuff is 3x squared. Now, I'm not done with this piece because that's my f prime. What do I still have to multiply that by? Right. And then I have to switch it up and do it the other way. Do you remember when you're using the product rule, there's always a plus separating the first two things multiplied together and the next two things multiplied together. Right? It's f prime g plus fg prime. So then I'm going to leave f alone. So it's just x cubed plus 1 to the 7th. And then I need the derivative of g, which is going to be the derivative of tangent of some stuff. So it's going to be secant squared of the stuff. And then what do I have to multiply by? Right, the derivative of the stuff, obviously, James, you said it 1,000 times. The derivative of the stuff, and the derivative of e to the x is e to the x. The derivative of x is 1. So things get a little bit messy sometimes. It's all right. Yeah, let's see, what time is it? Oh, it is 2:58. Bless you. Sure, let me do one more problem because I should show you one of those and then we'll call it a day. So sometimes you get chain rules within chain rules. Often. Here's kind of one of my favorite examples. Something like cotangent to the 5th of x to the 4th plus sine of x. And I like to work from the outside in, or really I like to think of what's my outermost function. And I know it doesn't have a very good name, but the outermost function here is being raised to the 5th power. Right? That's the outermost function. That's the thing you would do last. If you're plugging in some x, like pi, you would do pi to the 4th plus sine of pi, you add them together. Then you would do cotangent of that. Then you would raise that to the 5th power. Or more easily observed, if you just rewrite this as cotangent of x to the 4th plus sine of x, all raised to the 5th, it's relatively straightforward to see that, oh yeah, being raised to the 5th power is my outermost thing. And when I start differentiating, I've got some stuff to the 5th power. And my derivative is going to be 5 times my stuff to the 4th power. But then, what do we have to multiply by? Let's multiply by the derivative of the stuff. But the stuff is also complicated, right? It's not a straight, oh, it's a x to the 3rd, the derivative is 3x squared. It's another chain rule kind of deal. So we have to multiply by, sorry, I wrote that as 5x to the 4th. I apologize. That is 5 times stuff to the 4th. And then I have to multiply by the derivative of the stuff. Cotangent of x to the 4th plus sine of x. And you don't have to write it out in 2 steps like this, but you can. Right? You can be like, oh, it's the 5 times my stuff to the 4th times the derivative of the stuff, and then in the next step, actually write the derivative of the stuff. So we could totally then 5 times cotangent of x to the 4th plus sine of x to the 4th times. All right, now we're going to do the derivative of cotangent of some new stuff. And the derivative of cotangent of some new stuff is negative cosecant squared of the new stuff, x to the 4th plus sine of x. And then I have to multiply by the derivative of the new stuff, which is 4x cubed plus cosine of x. And that is how you apply the chain rule multiple times. We have a function of a function of a function. You're always multiplying by the derivative of the inside, And if the derivative of the insides are complicated, you probably have to use the chain rule for them as well, right? Here, my insides, my stuff wasn't just like some nice x cubed plus tangent of x, which we can straight differentiate. It's a function of another function, which we have to use the chain rule for again. There are like formulas for this, where you like the derivative of f of g of h of x is f prime of g of h times g prime of h times h. You shouldn't even think about that. You should just be like, I see some inner stuff, and I have to multiply by the derivative of it. And then when you're finding the derivative of this, you're like, oh, it's a chain rule again. So I'm going to use a chain rule again. So last word of wisdom here is try not to make it more complicated than it is. I'm not saying it's not complicated, because it is sometimes, but it doesn't have to be super complicated if you just kind of separate things out. If you look at the outside, it's like, oh, I just got this outer function being raised to some power, or being the sine or the cosine, or whatever the outermost function is. You're differentiating that. You're leaving the insides alone. And then you're stepping over here and you're multiplying by the derivative of the insides. And then you start the process over. If it's complicated, you start applying the chain rule again. We'll talk more about this next week for sure, right? We're not done with the chain rule. It's sticking around for the rest of your mathematical career.